Hey there, guys. Unit 3 and 4, I had to really think about that. Here's a video for 13F that you're going to watch during your cycle break. We're going to be looking into trees and minimum connector problems, stuff you've seen before already last year. We're going to be able to identify what a tree is, look for what's considered a spanning tree, which is trying to connect all of the different vertices via an edge of some sort, and then also find the most efficient way that we can do this, which is called a minimum spanning tree. And there's an algorithm which is called Prim's algorithm. Prim was a mathematician that worked alongside with Dijkstra, so I'm assuming also Dutch, and they really pioneered this computer science set of processes. It was really cool. So a tree is a connected graph that has no loops or multiple edges or cycles. This tree has 7 vertices and 6 edges, this particular one here. If I just move that one, here we go. The number of edges is always 1 less than the number of vertices if we're trying to adhere to the no loops or multiple edges or cycles. And a spanning tree is every connected graph will have at least one subgraph within it that is considered a tree, provided that it's connected. A subgraph is a tree, and if that tree connects all the vertices in the graph, this is called a spanning tree. Now this is important when we're looking into minimum spanning tree problems. A few key notes: a tree has no loops, multiple edges or cycles, has n-1 edges if it has n vertices, and a spanning tree is a tree that connects all the vertices of the graph. Now there can be more than one spanning tree or connected graph, so there's multiple ways that you can draw subgraphs, which are considered trees, within a giant graph itself. The total weight of a spanning tree is the total of all the weights on the edges that make up that tree. So this is another important feature which we'll look into for this example here. So let's draw one spanning tree for this graph shown. So in order to get a spanning tree, every single vertex has to be connected in a way that it doesn't create any loops or cycles. Now there are algorithms that help us with the weight part, but let's just assume that weight has no bearing or any influence in creating this. So maybe we can start at this one here, and I'll go specifically in a different color that really highlights it, maybe a yellow. That right there is a connection that we can make from this vertex to this vertex. Maybe this one here, another one here, some sort. Maybe we can connect this one over here on the top there. Now this is just one. I'm sure that you may have another one, but what's really important is making sure that we adhere to the specific criteria to make sure it is a spanning tree. Do that one, and maybe we can go one more. Yeah. Okay, so what we've done now is created a spanning tree. This too is criteria-wise ticks all the boxes. Every single vertex has some form of connection. It's included. We don't have any cycles, or we don't have any multiple edges of some sort. Okay, so there's no loops or cycles. If we were to draw this out separately, what we end up having is this kind of almost weird spider shape, disregarding the weights for now, which when copied out looks like that. It kind of looks like a person running, actually. That there is a spanning tree. B, calculate the weight of this spanning tree. So to calculate this weight, all the numbers here, the 3, the 1, the 3, the 2, the 2, the 4, this 2, and this 6 is added up. Quick math: 10, 15, 20, 22, this is 23. Now, 23 units, we don't know what these units are. This might be the smallest amount that we can get. Surely if we make other ones, they could be greater than this 23. And that's where we look into the concept of minimum spanning tree. And so a minimum spanning tree is to create a spanning tree with the lowest unit amount possible. Mainly used for efficiency's sake. Maybe you're connecting pipes or wires and you want to use the least amount, trying to ensure that every single vertex or substation is connected. So how this algorithm works: you choose any starting vertex. Any one will do because it has to be connected one way or another. And then you're gonna, once you've chosen that one, you're gonna inspect the edges starting from the vertex and choose the one with the smallest weight. So obviously that vertex you choose will branch off into different directions. Look for the one with the smallest. There might be multiple. So if there are two edges that have the same weight, it doesn't matter which one you choose one of them. The starting vertex, the edge, and the vertex that it connects to from the beginning and the minimum spanning tree. That gets colored in, and then you inspect all the edges from both of those vertices that you have colored in that tree, and then you choose the edge with the smallest weight. So it's kind of starting off, branching out to the smallest, and then looking at those two, branching off to the smallest, and then looking at those 3 or 4, branching off to the smallest. So it starts off small and then expands big. You just got to make sure that you don't create any type of edge, multiple edge or loop during that process. It's really good to just jump straight into the example. Apply Prin's algorithm to find the minimum spanning tree for this graph shown to the right. Write down the total weight in this minimum spanning tree. So we're going to start at any edge. Let's, for argument's sake, start at B. So we start at B. We look at all the different ways that this can branch out. So we have got a 2, a 6, and an 8. The smallest one from this one is 2. So this is part of the algorithm. There's A. Now done. Then from B and A, we're going to look at the smallest amounts. We've got an 8, we've got a 6, we've got a 5, and we've got a 6. 5 being the smallest. And we color that one in there. There is D. Then we just branch out again. We look at all the different connections. Now, if this 6 here was considered a small number or the smallest number, we can't connect that because then that will create a cycle within there, and that's what we're trying to avoid. We don't want cycles. It's being redundant. It's unnecessary. All right, so have a look. We have B has an 8. We're ignoring this one, so this one will create. So we cross over it. We have a 3 there, a 6 there, a 7 there, and a 6 there. 3 is the smallest one for D. So we branch it out. And again, we can't go from B to C because that will create a cycle. So this one is now out. You don't have to put a cross there, but I just, for the first example anyways, I like visually showing you that it's not necessary. We have a 5, a 6, a 7, a 6. So 5 is the smallest one here. And the last one that we have is this F, which is 2. Branched out. Now this has ensured that every single vertex is connected, and the minimum amount that we have completed is also taken into consideration. This adds up to 2 plus 5 plus the 3 plus the 5 plus 2, which is 17 units. This is the smallest or minimum spanning tree that we can create. Another example. Water is to be piped from a water tank to 7 outlets on a property. So we've got the tank that's in the middle, highlighted in red, and then you've got all these different outlets that branch out. The distances in meters, so now we've got some context, it's in meters, of the outlets from the tank and from each other are shown in the network below. Starting at the tank, the aim is to find the minimum length of pipe in meters, which will be needed to have water piped to all the outlets in the property. So on the diagram, show where the water pipes will be placed in order to minimize the length required. This is a very practical use of this because maybe there could be like a zoo of some sort that have water pipes connected. And obviously there are different ways in which placements can be for water pipes. We want to look for the smallest available if there are multiple choices. So using this algorithm, we have to make sure that everything is connected to the tank, and even though every vertex is used, maybe we can start at the tank. So the tank is our first one. I don't know why I'm choosing that. Let's go yellow. Tank is the first one. We're going to look at all the different outlets. We have 11, from the outlets rather, 11, 8, 5, and 2. So we're going to do 2. Then from these two, we have 11, and 8, and 5. And then for this one, we have 6. 6 being the lowest. We'll do that. So far, we've got outlet C done, outlet B done. Then branching out from here, we have an 11, we have a 13, we have an 11, 5, 8. 5 is the smallest. So we'll do out D. Can't do this one because that will create a loop. And then you just keep going on with the algorithm. Once the algorithm is complete, for B, you get your minimum length. Add all those numbers up and you get 44 meters. Remember, the context is in meters. Questions, only 23, which I've handed out to all of you. Best of luck on this one, guys. And I'll see you after the cycle break. See ya.